The central limit theorem is a very important idea in statistics. It's central to much of statistics. But before I get on to it, I just want to talk about some population distribution. This particular population distribution has a minimum value of 0 and a maximum value of x equals 100. Its mean is mu. Now mu is the balance point of this distribution. So it's the point such that if we imagine our distribution on a seesaw, our x-axis is a seesaw, then this point balances it. So the Greek letter mu is used when talking about population standard, the population mean. So mu is some value along the x-axis. The standard deviation is a measure of how far all the x values are from mu. So where the curve is high, like here, that means we have a lot of x values in this region. We've a fair amount here as well, but we've very few, say, in this region here, because the area is quite small. So the area tells us the frequency of x values in any particular interval. We can't really talk about a particular x value. We can't say what's the frequency of this x value. It doesn't really make sense, because the area under the curve at just one point is just this is 0, because we have the area of a line. The area of a line is really 0. We can only talk about intervals. So the proportion of x's in this interval is the area under the curve between this value and this value. So if we're getting standard deviation, it would involve calculus, because we have to multiply our frequencies by the square deviations of all our x values. So for a discrete distribution, it looks like this: sigma fi xi minus x bar squared. Well, x bar here would be replaced with mu. X bar if it's a sample, but mu if we're talking about population mean. So this is what we do if we had a discrete probability distribution, but this is a continuous probability distribution. So it doesn't make sense to take each x value and subtract the mean and multiply by its particular frequency, because its frequency is actually 0, as I said. The area of a line is just 0. So we'd have to talk about an interval of values. Basically we'd be talking about integration. We'd actually be doing an integral, which is not on the course. We'd be summing all the x values. Basically f of I would become f of x, where f of x is this function here, which in general we don't bother with. We multiply it by the distance of each x value from mu. So we're dealing with a continuous value of x, so we can drop that subscript I, and we'd integrate this quantity here from the lowest value of x, which could be minus infinity. Well, in this case it's actually 0 up to the highest value. So this is what we do. This is not on the course, but it's just to give you an idea of how we would calculate sigma. So this would be sigma. The Greek letter sigma is used to denote the standard deviation. It's actually a lowercase sigma. Uppercase sigma looks like this. That's for summing quantities. Now the size of our population is denoted by capital N. We could be talking about, say, the distribution of heights of a people in a particular country. Well, it won't look like this actually. Heights will look like a normal distribution for a particular age. Although if we're dealing with both sexes, male and female, height, we would have two normal distributions. This might be heights of males and this might be heights of females. It would actually be bimodal like this if we're talking about both genders. But anyway, that's just getting off the point. The general idea is that we have a population size n, which could be some gigantic number. Maybe think of a number in the region of 100,000, maybe more. And this is the distribution of all those values. But the values are along here. The values run from 0 to 100. So we have about 100,000 of these values. And this is how they're distributed. We're going to consider taking a sample from this population, because what we want to do is try to infer what the mean is. The mean, as I explained earlier, is mu. Mu is unknown. We're going to try and learn something about the mean. So that's where the central limit theorem comes in. So we take a sample of size little n. And let's make little n equal to 10. So here is one particular sample. So I'm sampling from all these x values here. Notice that when I take a random sample, I would expect to take a lot more values from in here than I would say from here, because we simply have a lot more values in here, because we have this area is much greater than this area here. So these values down here might be typically values in the range 15 to 30. So we might expect to get a lot of values in that range, but very few in this range here. That number is close to 100 because the curve is approaching the x-axis, so the area is approaching 0. So here's a typical sample that I just kind of made up, but I tried to imagine a lot of values in this interval, and I calculated the mean. Now the mean of a sample is denoted by x bar to distinguish it from the mean of our population, which is mu, which is unknown. So that's one particular sample. Now imagine throwing this sample back into the population, back into our population of about 100,000 values, and pulling out another sample. So we pull out another sample of size 10 and calculate the mean. Let's suppose that I get a value of 42. Now I'm going to call this mean x2 bar. And I keep on doing this. I throw that second sample back into the population. Then I randomly select another sample of size 10 and calculate its mean. I could call that mean x3 bar. That might come out to be, I don't know, say 31. So you imagine doing this for as often as you can, practically forever. And we look at the distribution of these sample means and see what it looks like. So here I've shown 3 of these sample means on this scale here that begins at 0. So I have 31, I have 39.2, and I have 42. Now we don't know what mu is, but well, in general we don't know what it is, but let's just say, just for this example, that mu is 43, or let's say it's 41 actually. Then we would expect our sample means to be bunched in around this unknown value of mu. So we'd expect them to be bunched in around 41, which, as I said, we don't know in general. We're trying to infer what mu is from our sample means. What we would actually find is, if we kept doing this process, we would find that most of our sample means would be bunched in around the unknown mean mu, the unknown true mean. That's the mean of the population, the underlying population. Most of them would be bunched in around this. So the distribution of our sample means would be a curve which peaks at 41. And it actually tails off on both sides as a normal distribution. This bell-shaped curve. So we'd find that we have a normal distribution. Well, not exactly normal, but approximately normal. Approximately a normal distribution with mean equal to the unknown mean mu, which in this case I'm just saying is 41, but we normally don't know what it is, and a standard deviation that's actually smaller than the standard deviation of our population. The standard deviation is given by the standard deviation of the population, sigma, which is usually not known either, because if we don't know the mean, then we can't know the standard deviation, because we actually need the mean to calculate the standard deviation. But anyway, the standard deviation of this distribution, called the sampling distribution, is given by sigma over root n. N is the sample size, so n in this case is 10. If I had a sample of size of 100, then the standard deviation would be sigma over the square root of 100, which means we'd have an even narrower distribution. So this distribution would give us a more precise estimate of mu. So we'd have a much narrower distribution about mu. So we'd be able to pin down what mu is more easily by looking at the means of our samples. So we'd have a sample of size 100. So this would be a sample of size 100. I'd have 100 values divided by 100 to get each of these. That should make intuitive sense. The bigger our sample size, the better we should be able to estimate our unknown mean. So it should be the case that our distribution narrows, so we'd have values even closer to our unknown value of 41 than we would have if n was small, say n was only 5 or something. But even if n is 10, even if n is just 10, then this distribution is a good approximation to a normal distribution, so that we can use our normal tables to do calculations. The amazing thing is, even if this is not normal, which it isn't, this is far from normal, this here, the distribution of our sample means, will be approximately normal, provided n is reasonably big. Even a value of 10 is pretty good actually. So here's the statement of the central limit theorem. If we take samples of size little n from a population with mean mu and standard deviation sigma, then the distribution of sample means is approximately normal with mean mu and standard deviation sigma over root n. So here's our population. Now the population doesn't have to be a normal. That's the fairly surprising thing about the central limit theorem. And these are our x values. So we take samples of size little n from our x values. We calculate the mean x bar. So these values here are not extra x bars for all of our samples, all the sample means. So we find that the distribution of the sample means is approximately normal. Its mean is the same as the mean of the population distribution, and its standard deviation is sigma divided by root n. Now, this distribution is sometimes called a sampling distribution. The approximation to a normal distribution improves as n goes to infinity. So as we let n get bigger and bigger, we get a better approximation to a normal distribution. Also, if the population distribution is normal, then this is exactly normal, this distribution.